The following lecture is a broad overview of the custom SAG analysis process. The intent of this lecture is not to teach you how to make your own custom SAG tool, although it is welcome and I would happily help you. It is meant to teach you that the general concepts we use to predict custom SAG, so you can understand where this might be coming from and how it may change. So, first, remember, cable sag amount can be counterintuitive. The more the cable sags, shown in yellow here, the less force is on the cable. This is because the cable is loose, and it also is due to the geometry of the cable. The less the cable sags, the more force is on the cable, shown in magenta. This is because the cable is tight. And this compounds because when you apply vertical force to a tight cable, the resulting horizontal tension is much higher and can go up to infinity. And I've drawn a little example here with the spreader bar showing, if you have two vertical cables, each component is going to be that weight component divided by 2. But if for any reason your cables are at an angle as shown, say take a 30-degree angle, that weight component or that tension in the cable doubles to each cable having the same value of W as cable tension with a 30-degree angle. Now, this is a simplified example, but it's just a reminder that depending on the angle, our forces can increase significantly. Now, how do we calculate cable sag? There are few ways to numerically predict cable sag. And remember, we need to predict this cable sag because we are analyzing the abutments under a total load condition, which we will never or want to see. We're not setting the sag like hoisting in design, so we need to predict it. And like any good engineering problem, we will start with our assumptions. So assumption number 1, the cable remains in the linear elastic region, so we can use Hooke's law. This isn't true in reality, and I account for this in my own custom sag tool by having a sliding scale of elastic modulus. But for the case of the explanation here, we'll say the cable remains linear elastic. In reality, the strands will settle and not be perfectly linear, and this is why we have that portion of our construction process where we let the construction stretch out and the cable sit for 24 hours. This helps us make sure that the cable is behaving closer to what our numerical prediction is like. The other assumption is that the cable sag geometry is parabolic. And this is a fair assumption under a uniform dead load. And for low sag cables, they can be idealized as parabolas instead of their true shape, which is going to be a catenary. Finally, I'll go into our method for calculating custom sag. So the general concept is that we are predicting how much a discretized 1 meter section of cable, discretized 1 meter sections of cable elongate over the whole span, and then comparing this to the elastic prediction, the PL over EA prediction of the total cable elongation that we get just from what the cable should be experiencing from a force perspective. And then we iterate a sag value until these two values match. So because we have more unknowns than equations, we need to iterate or use goal-seek to find our answer here. Now in the next video, I'm going to set up the problem and show you an example of how we would calculate custom sag.